All right, everyone. Welcome to our 11th lesson for Calculus 3 this semester. This video is to make up for the fact that we didn't have class last Friday here. So what we're going to do now that we are a little bit more comfortable with functions of multiple variables is we're going to begin discussing calculus of functions of multiple variables, a multivariable calculus. And we're going to begin doing that by studying the core of calculus, which comes from limits and continuity. Pretty much everything we do in a calculus class, you can trace back to a limit on some level. So we want to get comfortable doing limits of functions that have more than one variable. And first of all, we need to figure out what that exactly means. So to draw an analogy from Calculus 1, let's take a look at what a limit meant back then. We say that the limit as x goes to a of f of x exists if both the limit from the left and the limit from the right exist, and they are the same number. So your function has to agree as it's coming from the left as it does coming from the right. And then furthermore, we have continuity where not only do they agree on the left and right, meaning we have the overall limit here, but then that limit agrees with the actual function value. So we could be approaching a certain value, for example, but then the function value itself could be up here. So that would not be continuous. So we want to make sure what the function looks like it's going towards as x goes to a is what it actually hits at x equals a. All right, so to kind of illustrate the ways that this could not work, kind of like I was describing up there, there's a few ways that this could fail to be continuous. The first way is in which we could have a hole right here, and we could say that f of a does not exist. Another way that which we could be discontinuous is maybe our limits on the left and right don't agree. Just coming from this side, we think we're going to get a higher value than if we come from this side. And then finally, we could have the limits matching up, and we could have our function being defined, but the limit value, which would be down here, is not the same as the function value. So this would be another case of discontinuity. Even though both sides exist, they must not only exist, but agree with each other as well. So these are roughly the three different ways that we could be discontinuous. And this extends to multivariable calculus as well, only there will be many more versions of left and right than just two, as we'll see here in a moment. All right. Let's move on here. So let's talk about limits for a multivariable function. So kind of like limits for a single variable function, the limit means that as the point xy gets very close to a particular point ab, then f of xy gets very close to this particular number L. And in this case, the point AB lies in the plane, and there are infinitely many paths to approach the point. So it's not just from the left or right anymore. I mean, we could come from the left or the right and approach this point, but we could also come from below or above, or maybe we can even take some bizarre squiggly path. Maybe we could do a few loop-de-loops on our way to AB. So who's to say what's going to happen based on each path? Just like we could have different outcomes for the left and right with a single variable, we could have different outcomes maybe for all of these different paths heading to AB. And by the way, so this is going to, you might be like, okay, well this is still in 2D, how are we in Calc 3 right now? Remember that traditionally the third dimension, z, is going to be a function of x and y. So effectively what we're doing right now is we're looking at the xy plane, and this is going to be the domain of the function. These are x values that we're plugging in, or x and y values rather, that we're plugging in as we get close to our AB. Now, if we want to see that the limit exists back in Calc 1, all we had to do was look at the left, look at the right, and make sure they agree with each other. But now it seems like there are infinitely many ways to get to the point AB. So how do we test them all? How is that actually going to work? Well, we'll talk about that in a moment, but what's easier than testing them all is actually proving that the limit doesn't exist at a particular point, as we'll see in this example right here. So what I want to do is I want to calculate the limit of x and y heading towards the origin of this function here, x cubed minus y cubed, and then x cubed plus y cubed. So the first way I'm going to do it is I'm going to approach along the line y equals 0. Okay, so here's my origin. This is where I'm trying to plug in. This is the number I want to plug into my function or see what happens. I'm approaching along the line y equals 0. So I'm kind of coming in either this way or this way towards my point. And I want to see what happens as I come in from the left or right. All right, so let's see here. We have our starting limit here. So let's rewrite that. All right, now we know that the whole time we're approaching this, we're moving along the line y equals 0. So this whole entire time we're approaching our point, our y value is going to be 0 all the way there. So we could substitute in 0 for this y and then just focus on what x is doing, because we already know what y is doing. We just need to see what x is doing. So when I put zeros in for these, I have x cubed over x cubed. And then now we have a very easy single variable limit. These will cancel to give us 1. So if we approach along the line y equals 0, this limit gives us 1. Now that's not to say that this limit equals 1. You can almost kind of think of this as we found the limit coming from the left, for example. Like we found it going down one way and it's 1. Who's to say if we approach down a different path, we might get a different value? And that's what the second problem here is testing. This time, let's approach along the line x equals 0. So rather than coming from the left and right, we're instead going to approach this coming either down or up, like this. So we're going to approach vertically in some way. And this will be very much the same process that we just did. So we have our original limit. And then now, the whole time we're approaching, we're on the line x equals 0. So we could plug 0 in right here. And we have the limit as now y goes to 0, because we already used x, of negative y cubed over y cubed. Now this is also an easy single variable limit, but this time we end up getting negative 1. And because these two aren't equal, that means that this limit does not exist. So we can conclude this limit doesn't exist because we found two paths that do two different things. The one variable analogy is this situation right here, where we get a higher number approaching this way and then a lower number approaching this way. So we found two different paths to do that. And who's to say, maybe we could find some other paths that approach a third number. That's what makes multivariable limits a little bit more complicated, is that there's more than just two ways to get there. There's infinitely many. And maybe some of those are 1, -1, or maybe even some different numbers. But regardless, since we found two paths that don't match up with each other, we know the limit doesn't exist, because we need all of the paths to match up with one another. All right, so that's showing that a limit doesn't exist here. Unfortunately, we can't conclude that a limit exists just because we have two paths approaching the same limit. So suppose we went back to this problem here and we got 1 for both of these. So does that mean that our original limit is 1? Well, not necessarily, because maybe there's some new path that we didn't think of, like maybe coming, I don't know, diagonally or kind of curving in like this or what have you. Maybe one of those doesn't give us the same number that these two would. So unless we know what all of the paths do, then we can't conclude that it exists. And in general, that's kind of a lot more difficult to prove than showing that it doesn't exist, showing that it does. And we're not going to do too much of that in here. You need to use delta epsilon techniques in order to really do this. But we will take a look at a few of them, though. Anyways, let's do another non-existing one. Let's show that this limit doesn't exist. Now this time we're a little bit more on our own, because we need to come up with two paths on our own that go to different values here. So what I'm going to do, I'm going to start by picking the path y equals x. So what does this mean? Well, if I have my origin right here, remember this is still going to the origin, we're trying to plug that number in. Y equals x would mean I'm coming along either this way or this way. I'm kind of coming in diagonally. So let's see what would happen in that case. So I have the limit as x and y approaches 0, 0. And now what I'm going to do is, since I know y is always going to be equal to x, I might as well just substitute that in here. And that's what we're going to be doing each time. Oops. So now we have x squared times x over x to the 4th plus x squared. And then now we just only have x, so this is the limit as x is going to 0. All right. I know I can divide at least an x squared out of all of these, so I'll do so. And I have x over x squared plus 1. And then this is a continuous function at 0, so we can go ahead and just plug in 0. And we end up getting 0 for this. Okay, now if we can follow a different path and get something other than 0, we know that the limit doesn't exist, because then there'll be, then it does matter which way you go in. I'm going to do another path, and this time I'm going to follow along y equals x squared. So if this is my domain right here, these are all the x and y values I can plug in. As I head to the origin, what I'm doing is I'm following a parabola shape. So I'm kind of following in this parabola going towards the origin right here. And you are allowed to do that. These can be curved paths. They don't have to be straight paths right here. All right, so what will this do to our original limit? So if we begin with x squared y and then x to the 4th plus y squared, then what will we have now? Well, let's see here. So every time I see a y, I can substitute it in x squared. And we have x going to 0. All right, on the top, if I multiply these, I get another x to the 4th. And then down here, I have 2 copies of this, so it's 2x to the 4th. And then if I cancel here and take the limit of a constant, I get 1/2. Last I checked, 1/2 is not equal to 0. So depending on which path we decide to take here, we can end up getting 2 different values. So this means that our limit is not going to exist. Now remember, I want to remind you guys, this is something that's a little bit kind of confusing at first. Let's say I did get 0 for this. So let's say I got 0 from this limit, I got 0 from this one. Would that mean my overall limit's going to be 0? Well, not necessarily, because there's still a bunch of paths that I could approach. Like maybe I approach diagonally down this way or up here, or maybe I kind of squiggle in, like crazy and kind of just circle around it and go in. Who's to say one of those paths won't give me some different value? And of course, I can't actually check them all, so it's very difficult to conclude what this limit would actually be if it did exist. All right, let's continue on here. Now, the nice thing that we do know is that just like in Calc 1, we have limit laws to help us. In order to show a limit would exist kind of from scratch, we need to use epsilon delta, like I was saying, and that tends to be rather difficult. So what we're going to do is we're going to take limits that we know exist, like maybe limits of polynomials or things like that, and we're going to combine them using limit laws. So for example, if we have the function z equals c, or z is a constant, then the limit of that constant will just be the constant. And then in the same way, if I have the limit as x and y goes to a and b, and I only have an x, well, my x is going to a, so that means my result will be a. And in the same way, if I only have y right here, well, then as y goes to b, well, I'm going to get b right here. So this shows you that sometimes the multivariable limits don't have all the variables in them, but that's totally okay. Then you just look at the variable that they do have. All right, now this was saying, we were supposing that the limit as x, y goes to ab of f gives you L, and g is going to give you m. So if we have the sum of those two, well, then naturally the limits will be the sum or difference of the limits of the individual functions. And then a similar kind of thing goes here. If we have a constant, we can move the constant out of the limit, and then we get the constant times whatever the limit of the function went to on its own. All right, we can split limits over products just as we could in Calc 1, so we have L times M. And then we could also split them over division, L over M, although we need to note that M shouldn't be equal to 0. That's what caused us problems in our earlier problems there, and that's why they didn't exist, is because the M was going to 0. So in that case, we need to look at specially. But if the M is not going to 0, we can just go ahead and do these limits separately. All right, if we have a function raised to a power and we want to find the limit of that, we simply take the limit of the function on its own and raise that to a power. That's simply an extension of doing this a bunch of times with f. And then we could also have roots. So if we have the nth root of this, we have the nth root of the limit as well. And we need to assume this is greater than 0 if we have an even root, because we would maybe be doing a square root of a negative number. All right, so these are our basic limit laws, and I don't think any of these are particularly surprising. These are pretty much exactly the same limit laws as we had back in Calculus 1, only we're sticking a comma y next to all these functions. So I don't think any of this is too surprising here. All right. Now, one trick we can do to evaluate limits that do exist is we can use polar coordinates. So if we're heading to the origin, x, y is going to 0, 0, that means that the distance from the origin out to where we are is shrinking. So r is going to 0. So if we have some kind of path here that's heading in towards 0, notice that the r value for this path, the distance, is shrinking towards 0. And this is really nice because this is effectively having a circle that's closing in on our point. And since the circle reaches all the way around the point, it actually encompasses every single path going to the origin. So this is better because it gets all the paths. Because at some point, no matter what kind of insane path you have, like you're zooming around, if you come towards the origin, eventually you need to get closer and closer to the origin. So you could do whatever you want out here, that's all fine, but then eventually your r value will go to 0. So r going to 0 gets every kind of path, even insane looking paths like this. So let's use this and let's try to find the limit. Now let's remember from our Calc 2 days that r squared is x squared plus y squared. So now we can convert this limit to being r going to 0. And I see I have 2x squared plus 2y squared here. That seems like 2r. Meanwhile, down here I have x squared plus y squared. That will be r squared right here. All right. Oops, this is 2r squared. My mistake. All right, so let's take a look at this limit. We could use L'Hopital's rule here. So this is the limit as r goes to 0. And we're going to get 4r cosine of r squared divided by 2r. All right, well, this can simplify, and we end up just getting 2 cosine of r squared, and then we could substitute in r directly and end up getting 2. Now, unlike the other ones, you might be like, oh, well, that was just one path, but remember, this encompasses all paths, because you can effectively think of this as a circle shrinking in on our point. No matter which path we get, our distance from the path to the point is getting smaller and smaller as we go along. So this automatically covers all paths. So we know that every path of this will end up going to 2, so this limit exists and it's equal to 2. So this is one of the cases where we don't have to use delta epsilon techniques to get our limits for multivariable limits. This limit is exactly equal to 2. All right, let's try the same technique on another problem here. For this one, we need to remember that x is going to be r cosine of theta. All right, so this limit will turn into the limit as r goes to 0 of r squared cosine squared of theta divided by the square root of r squared. Now, r is a distance from the origin, so we're going to assume that r is going to be positive, meaning that this denominator will simply turn into an r. And then we can cancel, and we have the limit as r goes to 0 of r cosine of theta. Now, cosine of theta is just going to be some value in between -1 and 1. So we know that the limit as r goes to 0 of -r is less than or equal to the limit as r goes to 0 of r cosine of theta is less than or equal to the limit as r goes to 0 of just r. So I replace cosine with -1 here and 1 here. And since we know that both of these limits are going to be 0, well, then that means that this needs to equal 0 as well by the squeeze theorem. So this limit is going to equal 0, and remember, since this was r heading to 0 and we're going to the origin here, that means the overall limit is 0. No matter which path you took to the origin, all of them will give you 0, because we're shrinking in our circle, we're encompassing all the paths as we go in. All right, so there's some examples where we show that the limit does exist and what it's equal to. All right, so we talked about limits of multivariable functions. Now let's turn our attention to continuity of multivariable functions. So the definition for continuity of a multivariable function will be pretty much identical to what it was for a single variable. So if we have the limit of x and y approaching a and b of f of x, y, and that's equal to f of a, b, then we're going to be continuous. And note that this is saying a few things. This is saying that the limit exists and agrees on all paths approaching a, b. It's saying that the function value exists right here, and it's saying that the limit and the function value are the same. They're going to be equal here. All right, and then if we have some kind of domain D, which includes a lot of different x and y values, we say f is continuous on D if we're continuous at every point. All right, so now using the limit laws, what we can do is we can solve a lot of these limits by direct substitution, since the limit does exactly what you would expect. If we approach, say, x squared as x approaches 2, well, then we're going to get 4 for the limit, and we're going to get 4 for the function value as well. So for any kind of polynomial or something we know is a continuous function, we could just go ahead and use direct substitution. So I could plug in the numbers 2 and negative 1 here. So I have 2 squared minus 4 times 2. I have a negative 1 there. 3 times negative 1 squared minus 1. So I have 4 plus 8 plus 3 minus 1. Let's see, that's going to give me 14. So this limit's equal to 14, and I didn't even need to check a bunch of different paths because I know that if I approach x squared, that's going to be a continuous function. So it's going to do exactly what you would expect. The limit does exactly what the function would do at that point. All right, and then we could also deal with combinations of functions like this, where we insert a polynomial into some kind of square root. And if we have the square root function is continuous and this polynomial is continuous, so that means that we could plug in these directly into here as well. So this is going to equal 2 times 2 plus 3 times negative 1 over 4 times 2 minus negative 1. Let's see, this is root 1, and then this is 9. So we have 1/9 there. So all the limit laws that you're accustomed to in Calculus 1, where you can move limits in and out of square roots or other powers or logarithms or sines or cosines, all of those work here as well. All right. Let's see here. So now that we know what continuity is, let's talk about the continuity of this function. F of x, y is ln of x plus y. So we want to see where this function is continuous. Now, natural log as a single variable function is continuous so long as its input is greater than 0. And remember, if its input is 0 or less, then it's not just not continuous, it's not even defined at all. So we need to see where x plus y is greater than 0, and that seems to be when y is greater than negative x. So if we look at the domain D of our function, we draw the curve y is negative x. That's going to be right here. And so long as y is above this curve, so up here, then we're going to have a continuous function, because this would mean that we're going to have something positive in here, and log is continuous wherever its input is positive. But we can't go on the line or lower, because then that would be 0 or lower here. So it's going to be continuous everywhere above this dotted line, which is y is negative x. All right, let's take a look at the continuity of these functions, f, and then we're going to have g down here. All right, now when we look at f is what's called a piecewise function. It's one formula in one place and then another formula in a different place. Now this is saying that if we're away from the origin, we're using this formula, this rational function, for our f value. And this is saying that if we are at the origin, then we forget about whatever this is, we're just going to have 0 right there. So we need to know, is this function continuous? Well, first of all, this function is continuous outside the origin. So if we're in this mode right here, we're automatically continuous. And why is that? Well, this is a rational function, right? And rational functions, a polynomial over polynomial, are always going to be continuous so long as their denominator isn't 0. But as long as we're not at the origin, there's no way our denominator could be 0 right here. So we know we're going to be continuous everywhere at least, except maybe at the origin. Now, how do we see if we're continuous at the origin or not? Maybe we want to be continuous there as well. Well, remember, the definition of continuity says that we need our limit as we approach the origin to equal the value at the origin. So what we want is we want the limit as xy approaches 0, 0 of our function to be 0, which is f of 0, 0. Because our function value is actually 0 once we're at the origin, so we need it to look like it's going to 0 as well. All right, so let's evaluate this limit and see if it is 0. Okay, so now what we're going to do is we're going to use this formula here. And why are we using this and not just the constant 0? Well, as we're approaching the origin, we're not actually at the origin. And whenever we're using the function and we're not at the origin, we use this formula here. So we're really looking at this limit. Now, one way we could do this is we could substitute to polar coordinates, because this is the origin we're talking about. But another way we could do this is we can factor the numerator. We have x squared minus y squared, and then x squared plus y squared up here. All right, so we have this, and then conveniently, those can cancel out right here. And then now we just have this left over, but this is just a polynomial, and this ends up equaling 0. So since we agreed with the function value at the point we were approaching, that means that this is going to be continuous everywhere. Not just away from the origin, but also at the origin. So this is continuous everywhere in R2, or the xy plane. All right, now let's move on to a different function, g, which is extremely similar to the one we just looked at. It has the same formula here, but notice that the exception at the origin has now been changed to 1. All right, so just as before, we know that g is continuous outside the origin. And why is that? Well, it's for the same reason that we had last time. This is a rational function, and its denominator will never be 0 as long as we're in this region here. Now, what we need to do is we need to do the same thing that we did before. We need the limit as xy goes to 0, 0 of our function, or sorry, we're using g this time, to equal g of 0, 0, which is 1. Now, just as before, when we're approaching 0, 0, we're outside of the origin, meaning that we're using this formula here. Okay, now this is literally the same limit that we computed earlier. So we saw that this limit was 0, but 0 is not equal to 1. So what's going on here, we have that our limit does not agree with the function value at 0, 0. So what's happening is this surface is kind of leveling in to 0, but then once we get to the origin, it immediately just pops up to 1. And so that means that this is continuous everywhere except the origin. So we can't say we're continuous at the origin because we hop up to 1 when we should be going to 0 right there. So we're continuous everywhere except for the origin in this case. All right, well that about does it for multivariable limits, and with limits comes derivatives. So we will be seeing that in our next lesson here. We'll be learning how to use these multivariable limits to define a new version of the derivative for multivariable functions. All right, that's about it for now, so I will see you guys in class.